Hello, listeners. Welcome to the 5th episode of the Unlocking the Energy Trilemma podcast with our hosts Ravi Krishnan and Jose A. Martinez, JAM. Today, Ravi and JAM speak with Chris Bond, a 40-year expert in the energy sector who analyses real data to assess whether reality supports net zero ambitions. He contrasts how difficult it will be to replace fossil fuels with non-carbon emitting technologies. Before retiring, Chris worked in insurance risk engineering for companies such as Marsh, Willis, Swiss Re, visiting energy facilities in more than 50 countries. Ravi, JAM, over to you.
So, thank you, Ava, and welcome, Chris, for joining the Unlocking the Energy Trilemma. Thank you very much.
Thank you.
We always ask the same question to our guests. We ask them to give us a fact or a figure or a concept they want to highlight, which is related to the energy trilemma. Energy trilemma meaning security, sustainability, and affordability of energy. What do you want to highlight, Chris?
It's the discovery that I've made over the last couple of years that I had not realized before because I'm not a power engineer. But it is, and if I could refer to my notes, there can never be a surplus of electricity in a grid. I saw lots of remarks about, oh, we do this with the surplus, we'll do that with the surplus. There cannot be a surplus of electricity. It has to be in balance every second. So that's the responsibility of the grid operator. They have to balance supply with demand. And if supply is getting too high, they have to turn people who are supplying off. If supply is getting too low, they have to bring other forms of supply on, or they have to cut demand. The only way of getting country or area in operating in surplus is to be able to export or import across your boundary to another grid. So I think that's fundamental. The understanding of renewables needs to have that at the base.
Excellent. Chris, we've been reading a lot about net zero and how various stakeholders in the energy business are attempting to achieve net zero targets. Corporations have various net zero target goals. Countries have net zero goals. Financing is heavily dependent on some of their sustainability initiatives. Do you think net zero is achievable, especially since there are many pathways to achieve this? And if it is not achievable, can you throw some light on if it will ever be achievable and how?
This is what I started to investigate 2.5 years ago when I first started writing on my Substack, because I heard a lot about we're going to do this, net zero, UK passed laws, but I understood how dilute wind and solar are. And so I didn't think that it was going to be as easy as it was being presented. And I wanted to find out for myself. And so that's when I started crunching numbers. And the more numbers I crunched, first for the UK, then going wider to the US, California, Texas, the whole of the UA. I did a post on the upper 48 states, the contiguous 48 states. I've looked a bit at Australia because they are also rushing to transition. And wherever I've looked, the data that I've looked at, it just does not add up without huge, immense amounts of electricity or energy storage.
And can you tell us a bit about what were the significant findings of your research in terms of the various pathways to achieve net zero?
The biggest piece that is completely missing at the moment is affordable energy storage at the scale that you need to be able to replace significant part of the grids that we are used to now. Energy is prosperity. There is absolutely no question that the more energy per person you have, electricity is the most usable form of that, the more prosperous your society is. And that's why a lot of the countries which are trying to develop to benefit their populations are installing power stations like crazy. And the cheapest way of doing that is coal. And if we try and replicate that, and at the moment, the problem is we are putting a duplicate in place because we still need the gas-fired power stations, we still need the nuclear, we still need the dispatchable, reliable generation. At the moment, all the renewables are doing is putting a second layer on top of the existing grids and are costing a huge amount of money.
But this money we are investing to have more renewables, will it be worth it? Because if at the end of the energy transition the price of the electricity is higher than now, probably the trilemma won't be unlocked ever.
The one proven scale generation technology that we have and have had for decades is nuclear. It's carbon free pretty much, and it can be scaled, it can provide all the electricity that a country needs. And again, this is why China is building nuclear like crazy. And countries like the UAE, which have just put in 4 reactors, are realizing that, yes, nuclear, it costs a lot to put in, but then you design it properly, you can have that production for 50, 60, 80 years. Investment in renewables, I think the problem is we still need the non-renewables in the background to keep the lights on 24/7.
Yeah, you raise an interesting point about nuclear. Obviously, it does take at least 10 years to build a nuclear plant, and the availability of fuel and the potential safety measures if they're not administered properly. So there are some challenges. And of course, as you may have been reading, the development of SMRs is also currently it's expensive at almost $5 million a megawatt. But hopefully, with more and more SMRs being deployed over the years, that could address some of the same issues that you talked about. But just coming back to your point about energy storage, are you saying, is your view that currently energy storage is not available at long duration capacity, or is the round trip efficiency not high enough for many of the currently available energy storage technologies to make it a feasible option to complement renewable energy projects?
The biggest proven form of energy storage is pumped hydro, and Norway has a lot of pumped hydro. The UK has about 24 gigawatt hours. France has just built Nantes de Drance, which is 20-30 gigawatt hours. The trouble is pumped hydro has a quite limited power rating per installation. In Wales is 728 megawatts, Nantes de Drance is 900 megawatts. If you are looking at the scale of grid energy, the power flows, the UK in summer is about 25 gigawatts. In winter, it's about 40 to 45 gigawatts. And so you need hundreds of those pumped storage facilities to be able to absorb the power and be able to dispatch the power if you're going to replace all the coal or gas-fired power stations by intermittent renewables. You need the stored energy the numbers are just immense. And that's why I did California and Texas
Yes.
recently, to illustrate just how immense those numbers are.
You said in those reports that California would need 40 terawatt hour per year of long-term energy storage, and I think it was 50 terawatt hour per year in Texas. So they seem pretty big numbers, aren't they?
Not only they need those numbers of storage, 40, 50 million megawatt hours of energy storage, but they also need multiples of their current generation capacity. California, it was about 7. Texas, it's about 6 times its current wind capacity, as well as that energy storage. It's an enormous build out of the generation capacity, plus absolutely immense energy storage. Otherwise, you're not going to make the energy to support your society, and you're not going to be able to stop curtailment. And everybody is going to get very resentful of building all those assets at huge cost and then paying them to sit still when the wind doesn't blow and the sun doesn't shine.
And in fact, when California is promoted as a green state and they have gotten rid of thermal power plants in the state, however, you say in your reports that 60% of the imports, which is an important part of the electricity mix, are coming from thermal power plants from neighbors.
Yeah.
So it's not in my backyard, but thermal is still there.
And California has extended life of, I forget the name of the nuclear plant. California has extended the operating life of, I think, 3 gas power plants, because California has woken up to the reality that they cannot satisfy demand when the sun goes down, or when the sun starts to go down. Their peak demand is about 5, 6, 7, 8 p.m. when there's hardly any solar coming through at all. So California only gets about 25, 26% of its annual energy from solar plus wind. A quarter. That's where they are now. And their demand is going to go up because they're electrifying and everybody's building these gigawatt data centers.
You're absolutely right. And in fact, the lack of maturity of energy storage at this moment to offer cost-effective power has caused many markets around the world to take a look at their fuel mix and see what needs to be done in the short run. Take India, for example. I don't know if you've been following the news, but in the last couple of months, they just announced a big reversal in their policies and have announced the commissioning of 60 gigawatts of coal-fired power plants. And this was a country that was aiming very high in going green by 2030. The economy is projected to grow at about 8%, and they have no choice but to go back to their most abundant fuel, which is coal, to basically support the economic growth, largely because energy storage is not available in a scalable, long duration form at this moment, and they could not compromise economic growth. So I think it supports your argument that the technology is evolving at this moment. On that topic, would you be able to comment on the various types of energy storage technologies there? I know you talked about pumped storage, but what is your view on lithium ion and also other cryogenic storage or other technologies that are available, and how scalable and how cost effective do you believe some of these technologies are, and are they available for long duration?
At the moment, lithium ion seems to be designed for 2 to 4 hours. And the big installation in the desert of Arizona has got about 3.2 gigawatts of electrical energy storage with a load of containers from China, 3 vendors of battery technology from China, but they're all essentially lithium ion, the various chemistries. Lithium ion, I think, is good because it has sufficient energy density to put in a car, a vehicle, and give you moderate range and sometimes far too much performance compared with a gas-powered car. But lithium ion I see as being really a mobile technology. The compressed air energy storage is one which I've seen that the US Department of Energy reckons is currently the cheapest. The trouble is you have to have 200, 300, 400, whatever bar pressures when you've pumped the unit up. And I know only too well from risk engineering, you have cyclical pressures on equipment, and ultimately you wear the equipment out, you start propagating cracks. And if you store that much energy in compressed air form, if something blows, it will blow extremely violently. So you won't be able to have those anywhere near your population centers. You need distance from them. Liquid air energy storage has the advantage of being able to be stored at atmospheric pressure. You can have a tank, a vessel. LNG transport tankers are huge, and they can be built moderately cheaply. You use a lot of nickel alloy, I think, in the tanks, but you just need a heck of a lot of insulation around the tank to keep it cold. Liquid air could be built almost anywhere safely, because if it gets out, yes, it's immediately extremely cold, but your population centers are unlikely to be threatened by it. Vanadium flow batteries, I've seen a bit of a buzz about those, but vanadium, I understand, is extremely expensive, and therefore there is the problem that they're just not affordable at the moment. Energy and others developing iron-based batteries. Essentially, they allow it to rust in a controlled manner, and that gives up the energy, and then they reverse the rusting process when they charge it up. That's got the advantage of being very cheap raw materials, except they have to be made in very particular ways, and so that increases the expenses. So at the moment, we don't have the immensity of cheap electrical storage. Pump storage takes a decade to build. Not the Drance was about 2 billion US to build it. All of these things, there is no easy answer with any of them.
You didn't mention hydrogen. Is it a feasible option?
Chemical storage is interesting because you can store a lot of energy in the form of chemical. So if you can produce the chemical, then you've got energy and you're making artificial fuel, whether it's methanol, ammonia, whatever. The trouble is you waste a lot of energy producing hydrogen. Hydrogen is inherently very hazardous. It's also very inherently likely to escape your equipment, and it has global warming potential. So hydrogen is not an easy fix either. If you want to store a lot of hydrogen, and if you're talking about a state or a country, the only feasible storage place is salt dome. And geology for salt domes is in limited places. And that's why when I did my post on is hydrogen the answer, we've only got 1 or 2 areas in the UK. You would have to have your hydrogen production clustered around that storage geology. And therefore you have all the limits on grid capacity to and from it.
Yeah, I guess hydrogen can be quite case specific and location specific as well. To a great extent, it depends on the cost of renewables to generate, to produce the hydrogen and obviously the cost of the electrolyzer technology. And if one can overcome the conversion efficiency losses from power to hydrogen and then from hydrogen back to power, one could argue there is a case. But then, as you said, it can be quite location and geography specific. On the same lines of thought, a lot of what we've been talking about in terms of energy storage is utility scale energy storage. Behind the meter storage, and I know California is leading the country in terms of installations. Is that something that you find as a potential enabler for the energy transition? Do you see DERs taking a bigger and bigger percentage of the peak load?
I think if people personally choose to spend thousands or tens of thousands of dollars on a Tesla Powerwall or whatever they call them, and I understand a lot of Australians are also deciding this. They want to spend their personal money, but I think it's a very expensive way of getting a more level power outflow from their rooftop solar or whatever it is. It's usually rooftop solar that they're putting that in. So I think it's very expensive. And if people want to spend their money on it, go there.
Okay, Chris, I think we are arriving to the end. And thank you very much for all your comments. My last question, as we do with the rest of the guests, is trying to get a recommendation to unlock the energy trilemma, especially if we think that energy storage is so important to ensure the energy transition. But at this moment, and you are asking after a lot of years working in a risk engineering insurer, is not suitable in scale or in technology readiness, what do we do? How do we unlock the energy trilemma?
I think because energy storage is so critical, if you want to advance, you have to be able to capture when you do have peaks of potentially surplus renewable power. You want to capture that so you benefit from it when the wind stops blowing. And every night, people building solar and only solar every night, what are they going to do? Energy storage needs to be cheap, safe, hopefully built from common materials that standard fabrication systems can build, can produce in large volumes. Gravity storage is attractive in the sense that it is absolutely standard technology. You build a steel frame building, have a whole load of weights rising and falling and electric motors that can be reversed to generators. Something like that, which is dead common, really cheap to build. Anybody can build it, and you can build it almost anywhere, is the kind of energy storage that we need in huge amounts.
Thank you very much, Chris, for the time today. We answered a number of challenging questions here, and we will see how the energy storage market evolves. Certainly, regulations is also a key part to all of this. We need more clear carbon regulations that can motivate OEMs and technology providers to invest more, to make the technology more scalable and lower cost. But once again, we appreciate your views and thank you very much for your time. We look forward to another podcast with another expert in the energy transition space in the coming weeks. Thank you. Bye-bye.
Thank you very much. Goodbye.
We hope you liked this conversation. Follow us on LinkedIn or subscribe for free to the podcast on the platform of your choice: Spotify, Amazon, YouTube, or Apple. Because in the next episode, Ravi and Jam will speak with another expert in the industry to unlock the energy trilemma.